here's the deal today. I've cut off. We learned two. We can start. Take right now. All right, ready? Wait, where's Jake? He's not here. We learned two service concept theories already. One was exponential service single channel, right? The other one was exponential service multi-channel. Those are the two we learned so far. These two, constant service single channel and arbitrary service single channel, are the other two. So there's just those four that you need to focus on, and hopefully today we'll talk about several examples to help you realize which one you're reading about, so you know which formulas to jump to. I want you to write down page numbers. I should have wrote them up here. Economic analysis, let's say you only had just a limited amount of time to study, this would be what to study. There's no doubt, because this is truly what all of this is about, is being able to make a decision on how it will affect the company financially. Don't be wrong. There's those 6 calculations for each one of these services. We need to know there's a test a week from, 5 days?
No, it's a week from
Quiz?
today.
Okay.
What?
Quiz in 5 days. You ready? Hang on, where was I? Right here. What was I talking about?
Economic analysis.
Yeah, there was something right past
The
that.
six formulas that we need
Yeah,
to.
thank you. Casey's on.
But it took me a while. It's because the age is losing my memory.
No.
It took
At
me a
your
second.
age, it was just early drugs.
Pre-development, yes, yes.
Okay. These are the 6 for every one of these 4. Probability, probability, average number, average number, average time, average time. These are the 6, this is all you're going to concentrate on for all 4 of these services. Now, I like the formulas in the book. A couple of them are slightly different, but you get to the same answer. This one's so easy, you have all the cell locations, which, by the way, I just found this, and I'm thinking about posting it, but is that exact? I did those, look at the cell locations. You know, I did it exactly like the PowerPoint. So, if I post this, and you want to download it before the quiz, you got at least this one. But I would consider making that for this and this also, but the multi-channel, the amount of time it would take you to put a formula in to calculate that would just be way too long. You know what I'm talking about, where we looked at the chart instead?
Mm-hmm.
It's almost, if you do multi-channel, you would have a formula in for all of this, and then you hand enter this number by looking at that chart, which is why I want you to write pages down, because this is the one PowerPoint where I don't feel as confident with than any of the other chapters. That table on page 519. This is the key to a multi-channel. There's only one of them that are multi-channel. But solving that probability, that first probability of no units in the system, this is the key. Remember how I told you to use this? You got to use the rate of arrivals, the rate of service. Take the rate of arrivals divided by service, find that number as close to it as you can. Here's what your P sub O, probability of no units in the system, would be for 2 channels, 3 channels, 4, and 5 channels. And then you would just enter that number if you did the multi-channel for P sub O, and then the rest would calculate, if you decide to do that. But one time I did try to put the formula in right there, and it just took way too long. But I finally did get it to work, and I guess I didn't save it because I can't find it. I don't know. The only thing I think of is I put a lot of old stuff on my external hard drive, and maybe it's on an old semester from years ago, but I couldn't find it, and I don't want to do that again. So I would leave, if you decide to put this on Excel and this, this one I would just leave it blank and put the number in off the thing, and then the rest would calculate. It would still refer to that cell location, but I wouldn't put that formula in. And then what else did I want to mention? I don't know. Those are the 6 things. So, real quick, I'm recommending the PowerPoint for exponential service single channel. Slide 23. Exponential service single channel, right there. I'm recommending the pages in the book for exponential service multi-channel, which are pages 517, 518, 519. There's the 6 things, there's the table, okay? So there's that. Now, we're heading to constant and arbitrary, which share some formulas. And I really find it much easier if you consider using pages 526 and 527. Okay, on the left here is for arbitrary service. Look at the formula for the probability of no units in the system. It's just like single channel exponential.
What page is this?
This is 526.
Thank you.
This is the one for arbitrary that's different than all the rest because it's the only one that has the standard deviation involved. But it's easy. I mean, it's arrivals squared, standard deviation squared, multiply. Arrivals divided by service squared, add those together. I mean, it's not that hard. So you could set this one up too. Now, if you notice, the third one, average number of units in the system, L, which is so important when you're doing economic analysis, you got to get that out. Just like single channel exponential, just like single channel exponential for this, just like single channel exponential. So they're almost all alike except for that. Then, you're recognizing a problem as being constant service, which we're going to see an example here in just a minute. The only thing you change from these formulas is that one. The rest are exactly the same for constant as it is for arbitrary. The formula that replaces this one is right there. What page? 527? 527, right there. That's the formula for your L sub Q for constant. And that's the only thing you got to change. There's no standard deviation. Now, I'm not going to be tricky on the words. As a matter of fact, we're going to go through some examples. The words are going to be just like you see here, but not exact, but so close that it should be easy for you to figure it out. The average time a unit spends in the waiting line. Hey, what's the average time a customer might have to wait? Would you realize that's the average time a customer, is this wait? I'm sorry, spend in the line waiting, I guess. What's the probability that an arriving customer might have to wait for service? Probability here, time. The average number. What's the average number of customers that are usually in the system? So it's going to be, those are the types of questions you're going to see, which almost line up with the words exact. Most students, the biggest problem is figuring out which one of these 4 to use. So that's what I want you to kind of study the most. And then know where to go once you identify it. And then just plug the numbers in the formulas. It's that easy, really. But then, if it combines with economic analysis, you want to take this number right there, multiply it times the waiting cost, then take the cost per channel times the number of channels, add them together, there's your total cost. This question will probably say, hey, should you have 2 channels or 3 channels? So you're finding this for 2 channels, and then you do it again for 3 channels, and that's all you got to do because the waiting cost is the same. The cost per channel is the same. One's going to have 2 channels, and one's going to have 3 channels. It's this that changes for each one. Okay? All right? Are you ready to start with examples? Everybody realize what to expect? There are 4 of them. Economic analysis, where to look. I just want to review. What is it you'd be looking for if this is the one you're reading?
Standard deviation.
Very good, standard deviation. Once you see a standard deviation, you know this is the one. Exponential service multi-channel. Yeah, you won't have a K in the problem, but it will say you can't decide whether you should have 2 employees work at the same time or 3. Now, a lot of times on a quiz, there'll be a question maybe where it says, should you have this person working the channel or this person? And they'll think that's multi-channel, but only one's going to work at a time. The decision isn't about whether having 2 of them at the same time. It's one or the other. That's single channel and not multi-channel, and I don't want you to make that mistake because that's one of the second most common ones for this chapter. You got to say to yourself as you're reading it, are more than one person or channel going to be operating at the same time? And the moment you can say yes to that, go straight to that exponential service multi-channel because it's the only one of the 4 we're including this semester is multi-channel. and constant. You know, I hope it jumps out at you because the odds of a human being providing the service are pretty slim. That if it's constant, it's usually a machine or a robot or a process involved that takes the human out of the picture so the time doesn't vary. Usually. There's humans involved in some of these, but usually that's the case. That's why it's constant. Speaking of, let's go to for it. Oh, by the way, if it's not constant and it doesn't have a standard deviation and it doesn't have multiple channels, the hardest one to recognize is the last one that it could be. So just say by default, oh, this must be single channel exponential service. And that's kind of the hardest one for people to recognize. So do that one for last. Get the other three figured out, whether it's that and just process of elimination. All right, you ready? Here's constant. So you can see it in action. The mechanical pony ride machine at the entrance of the very popular J Mart provides 2 minutes of riding for 50 cents. Children wanting to ride the pony arrive, accompanied by an adult, blah, blah, blah. According to a Poisson arrivals for all 4 of them. You don't have to worry about what kind of arrival it is. The 4 we're learning all have Poisson arrival. Follow a Poisson distribution with a mean rate of 15 per hour. Time or rate? Rate. We don't have to convert this, right? 15 per hour is the unit of time. I keep emphasizing unit of time because when we get to arbitrary, this is so important. Unit of time is going to be a big deal in arbitrary because of that standard deviation. Standard deviation is in time, not rate. You've got to leave it in time. And it's got to be the same units of time that your rivals and your services in. So that's why it makes it kind of tricky. And odds are it won't be given to you in the same unit of time. So we go ahead, what does it say about service? Distribution, they arrive at 15 per hour. Oh, 2 minutes. Time. Let's convert it. If that pony were giving kids a ride every 2 minutes, one after another without stopping, an hour goes by, how many kids got to ride?
30.
30. Exactly. 60 minutes divided by 2 minutes for each one. There'd be 30 kids could do it if they jump on a rope one right after another. So we have a rate of 15 and 30. I always like to write it like this. Okay? We know it's constant because we know the pony is always given a 2-minute ride. No more, no less. It's a mechanical pony, so it can't really vary. Here's where we're converting the 2 minutes into 30 per hour. Utilization, idle. This is really probability of no units in the system, probability of someone has to wait. It's called utilization and idle fraction, but I won't call it that. I'm going to call it, what's the probability if there's no customers in the system, or the pony's not having to be, no kids want to ride it? Or what's the probability of kids walking up to the pony and they're going to have to wait for someone else to get off? That would be, the bottom probability. These are different calculations. What's happening here, what I want to point out is, where's L sub Q? You look at page 527, and you look up here, it's a slightly different formula, but gets you the exact same answer. This is the one that's different than arbitrary. This is constant, but all the other formulas are the same as arbitrary. What's odd, which gets a lot of students, is that why is it different here for the average number of units waiting compared to what's on page 527? It's just written differently in a different order, kind of. It's the exact same formula as far as the answer is concerned. We'll get you to the same spot. So use either one of them if you have a constant problem. If a problem that has constant service. And then where's L? This isn't even calculating it? So this person, like the question may say, what is the average number of children waiting to ride? Average number of children waiting, or customers waiting. And you look on page 526, the second one down says, average number of units in the waiting line, waiting. And that's arbitrary, so you go, oh, use the constant one or use this one. Okay? So that's how you match these up. I'm trying to get you ready to make this chapter the easy one of the two. It's impossible? What? All right, what is the average time a child waits for a ride? Don't forget, when you calculate this one, it's giving you the portion of whatever the unit of time is that you put arrivals and service when you entered it. So if our arrivals are per hour and our services per hour, this calculation is going to be the proportion of an hour. You multiply it times 60 minutes, because the question might say, It won't say, what is the average time a child is waiting for a ride in minutes, will probably. So you calculate this, but then you gotta do that last little step and turn it into minutes by multiplying that by times 60. Because there's 60 minutes an hour. This is the reason you know this is hours, because you enter the arrival per hour and the service per hour. So both of those time ones, the calculation will be in hours. We're heading to where we have some now coming up, they're gonna be per minute, arrivals per minute and service per minute. So when you calculate this, it's the portion of a minute. And you can convert that to how many minutes. All right, that was that one. Arbitrary. If we did all 6 numbers for constant, it'd be right there at 526. They're almost all like the exponential single channel. Very similar. Again, it's just that LQ is different for arbitrary and different for constant than the exponential. Here's our arbitrary now, single channel. This is going to show you the standard deviation. Remember what I just said though about standard deviation is the state and the time, and the time has to be the same units of time that you decided to make the arrival and the service. The person next to you can make the arrival and service per hour, and you can make it per minute. As long as your standard deviations, if that person's using the standard deviation in hours, and the other one who did minutes is making their standard deviation in minutes, you're both going to get the right answer. But that's the whole thing. Whatever, you don't have to put these in hours or minutes. You have choices. As long as you're consistent with everything that you have to enter is the same unit of time, hours or minutes or seconds. They have to be consistent. So here we go. The University Student Union has a self-service copy machine. On average, 12 customers per hour arrive to make copies. Convert or no convert? Not all at once, we're rolling. No convert, we're given to it as a rate. So far, it seems like the arrivals have all been given as rates, but don't assume that. Any of these times, you need to convert to rate. The arrival process follows a Poisson distribution. The time to copy documents follows approximately a normal distribution with a mean time of 2.5 minutes and a standard deviation of 30 seconds. Don't let that burn you. This is in seconds and that's in minutes. You gotta do some converting. You either gotta get them all in minutes, all in hours, or all in seconds. Whatever it may be, they gotta be the same. That's the note I'm writing. It's arbitrary. Arrivals and service and standard deviation all have to be the same units of time. Either hours or minutes or seconds. Whatever you choose, they got to be the same. What was our arrivals? 12 per hour. So we're at 12 per hour on arrival, but our service is 2.5 minutes. This is per hour. And then our standard deviations in seconds. So, we got to make a choice. What, minutes? Minutes. How do we convert 12 per hour to how many per 1 minute? Now realize this, it should be less than 1, because if we were helping one customer every minute, it'd be 60 per hour. So at 12 per hour, it's going to be a pretty small number. So what do you think the math is on that to convert that to 12 per hour to how many per second, or per minute, excuse me? Divided by the number of minutes, which is 60 minutes. So 12 divided by 60 equals 0.2. 0.2 per minute. Now this is not a rate, this is time. It's given to us in minutes. Is it really 2.5? It's given to us in minutes, but we gotta change it to per minute. So we can help one customer in 2.5 minutes. So in 1 minute, we are not even helping one customer. Do you realize that? Because it takes 2.5 minutes to help one customer. So 1 minute is going to be less than even half a customer, right? Because half of this time is 1 minute, 1.25 minutes is one customer, or would be a half a customer. We want to know how many in 1 minute. How do I convert 2.5 minutes to the amount in 1 minute? Divide by 60. So 2.5 divided by 60. Is that right? Hang on a minute. That's if we're doing seconds, isn't it? Someone jump in. Let's see what our answer is so we can.
So you take 1 divided by 2.5.
1 divided by, that's right. Thank you. 1 divided by the time will give you the proportion per the time interval that's in the denominator. So if it takes 2.5 minutes for one customer, then it's 1 over 2.5 customers per 1 minute. What's 1 divided by 2.5? Is it 0.4? So this was service. So this is 0.2 over 0.4. This is in minutes. That's in minutes. 30 seconds. We have to convert it to minutes. 30 seconds is a half a minute. So now our standard deviation is 0.5 minutes. This is in minutes, this is in minutes, this is in minutes. We're now good to go. And you just jump to the formula arbitrary and you start filling them in. It's that easy. This is the hardest part. Recognize which one it is. Doing the little, this is the hardest one to convert of all of them, by the way, because of that standard deviation. It's got to stay in time. It's got to be the same time interval that you decide to make these. Because we're going nice and fast, let's just, for the minute, go with hour. Let's just do this again with hour. This doesn't need to be converted at all, right? 12 per hour. So we'll go, we know what 12 is up here. 2.5 minutes, every 2.5 minutes for 60 minutes, 60 divided by 2.5.
Okay, question or test, can we convert it anywhere we want to?
Any way you want to. That's the whole
You're
point.
not gonna have to.
As long as they're all the same. This one gets most students because of this darn standard deviation. I keep telling you which problems I've seen semester after semester because I want you guys to not make those same mistakes because these are the most common ones that just for some reason seem like they're really easy to make. So I'm really emphasizing them the most. Tell me 60 minutes, 2.5 minutes each one, divided by 2.5, 60 is how many? 24 on those? 24. All right. But this is 30 seconds, and this is in hours, and this is in hours. We got to turn what portion of an hour is 30 seconds. If it's a half a minute, then it's, help me out, 1/120th of an hour? Nobody's jumping on that one. How are we doing? Come on, how are we doing this?
You'd have to, because 1 minute is
Take
1/60th
60
of a
minutes,
minute.
yeah, there we go. Take 60 minutes times whatever 1 over 120 is, that's 0.0 something something, and see if you get 0.5, right? That'd be 120, 60 divided by 120. So what's 1 over, so everybody see how we did this? 30 seconds is a half a minute. You gotta turn half a minute into the proportion of an hour. Well, how many half a minutes are there in an hour? There are 120 of them. So this is 1/120th of an hour, because you gotta leave this in time, not rate. So that's why I didn't divide by, or how many would be in 60 minutes if one were every a half a minute, that would be 120, right? But it's gotta be left in time, so it's 1 over 120 of an hour, which would be, calculators, what's 1 divided by 120? 0.0083? 83? And we're rounding correctly? Okay. Now that's your standard deviation in time. Because that's how much of an hour. So it's 12, 24, 0.0083 will give you the exact same answer if we did our math right. That, where's this one? 0.2 over 0.4, and this is 0.5, you'll get the exact same answer. Because they're all in the same consistent time interval. And that is going to tell us what's the probability of no use in the system. Remember when I said economic analysis is one of the most important parts because a lot of decisions are based on that? I want to point out one other thing. Where's it at? It's not even on there. Darn. We're going back to page 5.6. All of these, you have to calculate the probability that an arriving unit has to wait. This is probably the second most important calculation. So many businesses that I've worked with focus on this because they're so concerned about customer service. And most businesses will say, oh, I want this to be, if they have some competition, they'll say, I want this to be 10% chance or less. If a business has like competition all over on the same road, I want this to be 5% or less. And if a business doesn't have competition, they're like, what do you mean that 65% chance of customers? How about this? Secretary of State, What do you mean that's 99% chance the customer might have to wait? Well, that's okay. We're not gonna add channels. We're in the state of Michigan. Everybody's got to come here. We don't even have competition. You have to get your driving license here. You have to get your tags here. You are going to wait. This should be 100 par, huh? But in business, even if you don't have a lot of competition, most are still at 60, 70 or less. I haven't seen many companies ever say, you know, if they know, even if we're, you know, even if they have to wait, they're coming back. We're the only ones in town. They're not going to drive 100 miles to get in. They're coming back. And so the cost of not providing the best customer service isn't so expensive in that case. So that's the second most important one. A lot of companies will focus on this. They don't want they want that percent of a customer having to wait to be as kind of lower, even if it means you have to add another channel and take on that cost. So those are the two most important ones. All right, those are examples. Now here's another example. I posted almost every one of these. Let's talk about this one. We have not talked about this one. Here we go. You ready? Let me make sure there's nothing there to give it away. All right, hang on. Quit looking. Darn, how am I going to do this? I don't want you to see the answer yet. So don't open it up either. Okay. Darn, it's not fitting. Hang on. I'll get it. You ready? Okay. Oh, good. All right. That worked out well. And that was just the company has tool cribs where workmen draw parts. Okay? They come in, they have to check out the parts. 2 men have applied for the position of distribution of parts to the workmen. George is fresh out of trade school. He expects $8 an hour. This is an old question. What's the minimum wage now? He expects what is it? $9.25 is minimum wage. So this is less than minimum wage. This is how old this is. He expects $8 per hour salary, or hourly, I guess. His average service time is 4 minutes in providing the service. John is a veteran who expects $12 per hour, and his average service time is 3 minutes. Does it faster, would have to cost us more money. A workman's time waiting for a part to be distributed to them is figured at $10 per hour, so it's not that big. Workmen arrive and draw parts on an average rate of 12 per hour. There's your arrival rate. You ready? Which one of the four? Just tell me the service, because they're all points on arrivals. I couldn't hear you. I heard it sounded like you were correct. What kind of service? Arbitrary. Arbitrary. Is there a standard deviation? Can't be arbitrary. This is why I wanted to do this. And go ahead. What'd you say? Is it single channel?
No. Yeah, because you're comparing.
Thank you. Very good. That's okay, Sean. That's okay. I didn't take the points off. Yes, you're okay. Right? No, yeah, that was a joke.
Only me.
Guys, it was a joke. If I said to Alex, she's all so mad at me now that if I would have said it, you're not mad? Okay, all right. All right. So I could make a joke? No, I better not. That was it right there. Let's go back. You ready? I've got a waiting cost of $10 per hour. I've got a $12 per hour, arrival rate of 12 per hour. But we have two different service rates, and this is single channel. The reason it's single channel, only one's going to be doing the job at a time, not both of them. Your decision on which one would you hire. Can you justify spending the extra? It's not that it's an extra $4. You got to look at it as what percent. That's an extra 50% in pay. You got to look at it that way, which is a big deal. I'll change these numbers someday. But it's an extra 50%. Is it worth it for a savings of 1 minute? The only way to truly know which is the best financially, you'll be happy with either one of them, is to do the economic analysis. So you have to calculate what? Give me the letter or the name. You have to calculate what. We already got the waiting cost. We got the cost per channel. What? VL. Put that. If you can't remember that, I don't know, do a font 24 with your pen. Economic analysis must calculate L. That's the biggest part of it. You're given the waiting cost. You're given the cost per channel. You're given the number of channels. It's the L that it's all about on this economic analysis. Tell me which one based on total cost. right? You guys, if any of you missed the lecture 2 days ago, please watch the video because this is one of the harder chapters and you missed a lot of really good stuff.
You said you're gonna post these?
I have posted.
You have posted that?
Yes, I have.
With the answer?
Yes, we're about to see the answer. I want us to talk about how we'll get to the answer before we see it though. You'll have to calculate L for, what's his name, George? And then you gotta calculate L for John. And the reason they're gonna be a lot different is because you have a different service rate for each of them. Arrival rates are the same, which is 12. Now, let's do John and, well, I'm sorry, George, and then let's do John. What will be George's service rate? What's the time for George? 4 minutes, and this is 12 per hour, so an hour every 4 minutes means George can help how many? Am I doing this right? Is George 4 minutes?
Yeah.
Okay, how many? What's 16 minutes divided by 4? Help me out. 15? No, that's not 15. 12 and, 7.5? Is it 15? Thank you. I'm sorry, I had a question. George is 15. Give me Josh. What's John's rate? I can't hear you guys.
You wrote 30, but she said 15.
3, John is 3.
What do you mean?
You
where's
wrote 30.
Oh, thank you. Okay, please give me John. 20. So he's 12 over 20. 12 arrival, 15 service, 12 arrival, 20 service. Just look what else. They're both going to be a waiting cost of $10, and then the cost per channel. Cost per channel. George has a cost of how much per channel? 8. And what's John? 12. Okay, so in George's case, we've got $8 times 1 channel plus L times, where's the waiting cost? 10. This is George. For John, we've got $12 times 1 plus L times 10. It's that easy. All you gotta do now is plug that in. This is how I would attack these questions that are asking about money. Because I would get all the way to this point and say, okay, I know exactly what I need. And then you go to, I'm going to page, give me the page number for single channel exponential. 512. But thank you for trying. Here we go. Right, almost.
Where did my time go?
Maybe I got it wrong. It's possible. You ready? What do I do first to get this L right here? What should I do? What will be the first thing I do? What? L sub Q. Okay. What's the number on top? Let's do George. What is that squared? What's being squared at the top of L? Everybody, we're at LQ, because we can't get L without LQ. So LQ has something squared in the numerator. Arrival rate squared. This is George's. So this is 12 squared, whoops, 12 squared over, what's the service rate? 15 times 15 minus 12, is that it? Okay, 15 minus 12 is 3. 3 times 15 is 45. 12 divided by 45 is 0.4, help me? 12 divided by 45. Not one person's calculating. Oh, I'm sorry, I forgot to square the 12. Thank you. Was 144 divided by 45. Excuse me. Did I get this part? Yeah. 3.2. There's the L sub Q. Now take L sub Q, 3.2, add arrival divided by service, 12 over 15 is 0.875? 0.8. So I got 3.2 plus 0.8 equals 4. There is George's. Let's get George. 1 times 8, 4 times 10, 40, $48, right? Because this is 4 if we did this right. Correct? Everybody see what I did? Now we're going to do it again for John. And instead of doing it again, I think we all figured out what's going on. Wow. Come on. Ready? Blah, 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 blah. L sub Q, 12 squared, 15 times, 15 minus 12, 144. Divided by 45, 3.2. Take that, add this, 3.2 plus 8. George is at a 4. Plug in the 4. Where's George? Boom. 8 times 1, 10 times 4, $48. Now we jump to John. John is 12 arrival, but 20 service. 20 minus 12 is 8. 8 times 20 is 160. 144 again. 0.9. Take 0.9, add 12 over 20, because he has a different service rate, which is 0.6. 1.5. So now this L would be 1.5 for John. 1.5 times 10 and 1 times 12, because he had $12 an hour, is $27. Wait a minute, what is he? 48, that is a big difference. Who are we hiring? But John's more expensive. Wait a minute. I want to tell you something. If you're ever a manager and you want to justify hiring the more expensive person, if you can truly come up with a good waiting cost and it's fair, this is a great tool to get upper management to give you the permission to hire the more expensive person by them seeing the reality of that, how much faster this, even though the cost is 50% higher for this person, because of that 1 minute savings in time of that experience, it brings our true hourly cost down significantly. So please, let me hire the more expensive person. We'll save it in the long run than waiting. You're on. You proved it.
So how are you supposed to figure out what their waiting time is?
Now that's the part you're not learning in this class. That's really the hardest part. What that cost is right there takes meetings and gathering all kinds of information to know exactly how a customer would react if they truly waited too long. Would they come back? Would they be upset? Would they never come back? And what would be the cost? What's the average amount a customer spends? You got to know that. Each customer spends $40, so we would lose $40. How often, do they come?
What class do we do that?
I haven't found one. I don't know. You got to go on the internet now to learn. Well, thank God you guys got the internet, the best invention of our lives, because I didn't have it back then. Did I tell you what the internet was like when we first got it? I was working at this company, and the internet finally just got out. And we're all going, and it's just this red letters, just writing. You hit these little pluses, and you can read more. No graphics, one color. You could put it in the web page, and it's just, there'd be these titles, and you could just read more. And it was so boring that hardly that many people really utilized it, unless you really wanted to dig for some information. And then all of a sudden, the 1990s, I think, is when it happened. HTML got invented, and all these pictures and colors arrived. Oh my God. The internet is totally different than it was. And it took off like a lightning bolt, and it's part of our lives forever now. And soon we'll be able to just have the tapped in from our antenna hooked into a certain part of our brain where we can just think and Google it. Or duck, whatever, go it. Does everybody know what I'm talking about? No one knows? That's the new search engine of the future. What was your question, please?
So, what is John worth then? So obviously, John is worth more than what he's currently making because of his.
Well, that's one way of looking at it, but.
Right, but what I'm saying is, so at some point John's going to come to us and say, "Hey, I want a raise," and then we can say, "But if he were to increase 1 more minute of productivity,
I always said that
exponentially."
if you're a good manager, there are ways to keep employees motivated without having to give them more money.
Sure.
And so what my whole thing was, I knew from it as an employee that it wasn't time for raises yet, because a lot of companies will only do them once a year. And so when I started to lose one of the 5 keys to happiness career, like not feeling challenged anymore, or not respecting the person I work for because they don't know what they're doing, or something like that. There's these 5 keys in the job. At that point in time, what would motivate me again is new duties, or like a challenging project or something to keep my interest. And that's what I then used with employees also. And it actually is a great tool, because a lot of times when employees start to hate their job is because they're slightly bored. And so challenging them with a new project that maybe you can get part off your desk even ends up being a win-win.
So this screen right here is just economic analysis. It's not showing us.
It's showing you how to get the L sub Q and the L. Now, this question may have 3 parts. It may say, what's the average number of customers, can't think of the word, what's the average number of customers in the waiting line? And then it will say, maybe say, what's the average number of customers in the system? Which one would you hire based on total cost, which is the economic analysis. That's total cost, meaning the cost of the person and the cost of waiting. Cost of the person and the cost of waiting.
So each question, like, wouldn't have all six of the questions?
No, none of them will have all 6 of them. Most of them will only have 2 or 3. You just gotta line up which one's being asked for to which one of these 6, and the words are gonna be semi-obvious.
And then you need to know when to.
When you do economic analysis, you'll see the words just like this. Where is it here? Which applicant should be hired? And when you start seeing the waiting costs in there, usually the only reason you're given the waiting costs is you need to do an economic analysis. All right, let's do another one.
Mr.
I'm sorry, let's keep going.
So if you asked us which guy would you hire?
You say, no, George was $57. You want to save money.
48 and 27.
I can't remember. Thank you. George was 48. John was 27. You want to hire the lesser expensive one. Even though he's $12 an hour, he's saving you so much money by not having our employees wait.
Okay, well,
Because every time an employee waits, it's costing us $10 an hour because they're not doing their job. Yeah, he's faster, but costs us more. He's slower, but costs us less. It's not always, it could be either one, but in this case, it's obvious that spending more money, $12 an hour, would save us money in the waiting cost of our employees having to wait for things because he's so much faster. Okay? Yes?
Is it the 1 cent for 1 hour?
This right here?
Yeah.
That means one channel.
1 channel.
We're only putting in, it's always the cost of a channel times the number of channels, but we're only putting either one person in or one person in. This isn't multi-channel, but you still need a 1 there to know there's one channel. The formula is cost per channel times K. In this case, K is 1 because only 1 works at a time. Waiting cost times L. And we have to calculate it. Go ahead, Sean.
If we were using the Excel spreadsheet, how would we go about showing you?
If you use Excel, you need to transfer some of that onto your paper, and then at the end of the quiz, get my attention, let me watch you turn on the internet, and email me the spreadsheet.
Okay, so it's like, because I can, look through the Excel spreadsheet, do the first 2 steps, then total cost.
Yeah, right. Once you have this rival and you convert it to get the service rate,
Right.
you can get your L.
Right.
Exactly. That's right. What you might do is say, okay, let me go to that cell location where L is, and say, oh, it's G5, and you just put whatever's in G5. That way you can convert it right on the paper as to how you got that number. Or you can send me the spreadsheet, but you need to put something on the paper.
Right.
Okay? All right, let's do another one. Can we do another one?
yes.
Okay, here we go. God, I'm glad I'm showing you these. I didn't realize you guys had this many questions. I gotta turn this off. I don't want you to see the answer. Hang on. What is going on? Here we go. Hang on, how do I? Oh, this is okay already. Ready? You have some numbers here. It says 2 different applicants are being considered for a customer service position. Darn, this is almost too much like the other one. One is Frank, and he has a limited experience, which is spelled wrong. Darn. And can be hired at $15 an hour. It has an average service rate. Wow, service is the first one the service is given to us in rate. Has an average service rate of 6 customers per hour. The other applicant, Tim, has more experience and can service customers at 7 per hour, but this applicant would have to be paid $22 per hour. Assuming customers arrive at a rate of 5 customers per hour, the company has assigned a customer waiting cost of $12 per hour. If I scroll down and say, which one would you hire? Exactly like the other one, more recent numbers. This must have been one I've written more recently. Everything's the same. I don't even know why we would even, but realize how easy this is. I just looked and realized you don't have to calculate anything except for the economic analysis. Everything's in front of you. Everything's there. This is one you can do in seconds. What is it you look for other than the waiting cost, other than the cost per channel? What's K? 1, because it's either one or the other. It's not both. K is 1. We got a cost per channel. We got a waiting cost. What else do you need? L. Where's that? It's being given to you. Now, I've given a problem like this on the quiz, and because L was not the 4th one down, there's students, actually more than you would think, because they say, oh, L's always the third one down or the fourth one down, whichever it usually is, they'll give me that number instead of looking at the names of these. And really, L is the average number in the system, and it's not the third one down here, it's the second one down. So don't go, oh, on the PowerPoint, the third one down, and think, oh, this has gotta be it, because really it's that. Know what you're looking for, L, the average number in the system to get to that academic analysis. So this is a very easy one to do. You don't even have to calculate out. Let's get another one. We don't even need to see this one. Doesn't this kind of look like it? Oh, wait, stop. There's the answer. This is better. Hang on. I gotta figure out how to make it easy to see. Hey, where's the question? Okay, this is just an answer to a question that's in your book. So let's go to number 10 on page. Here we go. Looks like it's page 537. Why is this not? There's something going on here. Everything's on it. But it's not on the screen because you got to hit this other button. All right. Here we go. It says, Trosper Tire Company decided to hire a new mechanic to handle all tire changes for the customer ordering a new set of tires. 2 mechanics applied for the job. This may be too close. Let's keep going. 2 mechanics applied for the job. 1 mechanic has limited experience, can be hired at $14 an hour, and can service an average of 3 customers per hour. The other mechanic has several years' experience, can service an average of 4 customers per hour, but must be paid $20 an hour. Which of the 4 is this service? Single channel.
It depends on what they're asking.
You're saying because it's not constant? You're saying because there's no standard deviation? What is the service, first of all? If it's a human involved, you're probably could be pretty confident it's not constant, you're right. Is there a standard deviation involved? So it is a single channel or multi-channel? Single because only one or the other, right? So it's got to be exponential. We've already just looked at 2 of these. I actually there must be something about this that changes because the answer I have is not for single channel. Oh, yes, it is. Darn, I just read the answer. All right. Here's what it looks like if you were to calculate which number would we use for the economic analysis for the first employee who has a service rate of 3. What's the number? 2.0. You went straight to the L, right? And then the other employee would be a 1. The story said that the new mechanic would be $30 waiting cost. $14 an hour times 1. You just don't see the 1 there. Waiting cost of $30. L from this employee is a 2. Total cost, $74. The other employee, we're using an L of 1 times the waiting cost of $30, but their cost is 20 plus 50. This is just like the first example. It just so happens the more experienced one, which is a significantly higher price per hour, ends up saving us so much in waiting costs because it's half the amount of waiting involved that we're better off spending the more money in this case. In real life, I would train this person to be as fast as this person because I'm that cheap. All right, let's do another one. Hang on, I want you to see this. All right, I gotta move it smaller. We see the whole thing? You ready? Oh, what's that underneath? That's nothing. Oh, we've seen this one. You ready? It's literally telling you, darn it. You're trying to decide between 2 or 3 channels of service, 2 or 3 employees or whatever it's going to be. The arrival rate's 2.5 per hour. It's not many arrivals. The mean service time per channel is 10 minutes, which would have to be converted. The waiting cost is $25 an hour. The cost per channel is equal to $16 per hour. Show your work manually to calculate total cost per hour for 2 channels, and then again for 3 channels, then tell which is best. This total cost per hour is the words that you were asking about that tells you to do the economic analysis, plus Mick, the fact that, where's the weighting cost? The fact that it has a weighting cost right here at 25 is another hint that you're probably doing economic analysis, which is what you asked about. And we saw this one 2 days ago. And so this is posted. You know to do, here's the thing, in order to get the L on this one, you need that piece of O. It's the only one you have to have the piece of O, the probability of no orders in the system, to get to L. There's 3 calculations because it's multi-channel. But you know what you got to do, right, to get the piece of O. What divided by what? What's the arrival? 2.5. What's the service? 2.5 over, is it 6? 60 minutes. Divided by 10, 1 every 10 minutes means 6. 2.5 over 6, calculator, Trevor, you're not counting this time. 2.5 over 6. We're going to the chart on page 4.16. Really? Is that true? 0.416. There we go. 0.416. We're going to page, I can't remember. Jumping 8 times at the page.
519.
Thank you. 519. We're 0.416. We're getting as close as we can to 0.416. I'm going to go with the 0.40. When we calculate this for 2 channels, I got to get up here. Oh wait, are they the same service each? They're different services. So we're only doing 1 person right now? No. The service is the same, isn't it? Yeah. Okay, service is the same. Good. We can do both right now. 0.4. When we calculate the piece of O for 2 channels and get to the L, we're going to use, I can't tell from this angle, is it 0.6667? Is that the one that lines up?
Yes.
For 3 channels, we're going to use 0.6701. They're so close to each other. This isn't going to have as much of an effect as some of the other ones we've done. But those are the 2 numbers we use to do this. We now have, for both 2 channels and 3 channels, this number already. We use the one for 2 channels to calculate this and then this. Then we use the one for 3 channels to calculate this and this again. And then we do our economic analysis. This is the only tough part right here. And you realize the multi-channel, you knew to go to this page, you knew you don't calculate this, you look it up, but this you calculate, and then economic analysis, because this is all you need. You're given the weighting cost times this, you're given the cost per channel times 2, and then you do it again with the cost per channel times 3 channels. So that cost per channel, which was $16, that's $16 times 2 plus 25 times the L for 2, then it's $16 times 3 plus 25 times the L for 3. I know because those L's are so close that this times 3 is going to have a major effect compared to times 2, which tells me 2 channels will probably be the best decision. Let's take a look. Watch me be wrong. And tell by Sean to look at his face that I'm wrong. He's so happy.
Oh, because I understand.
Oh, okay, just check. You ready? Because you understand it. It is 2 times 3 times. There's the L, there's the L. Wait a minute. You guys, wasn't it 0.4? Oh, we did a little adjustment because it wasn't exactly 0.4. It was 0.416. But still, look how close they are. They're still pretty close. There's the L, there's the L. They're both 25 weighting costs. This is what's affecting it. So here's a situation where we're recommending going with 2 channels. Of course, you always got to compare this in real life to the probability of a customer waiting to make sure that you really want to do this. Because if the probability is too high, then you say to yourself as a manager, is it worth the extra $16 per hour to provide, to take that probability of a customer having to wait too long down significantly? Because it will take it down significantly with 3 channels compared to 2. So you can also, in real life, do those 6 calculations to get to that probability of a customer having to wait to compare to this. Make sure this is the best decision. All right, I think I got one more ready. What is this? What is this? Come on, what is this? What is this? It's either known activities, uncertain estimated activities, or what's crashing, or crashing. Is that what you said? Oh, I wasn't sure what you said. I should start with a C or okay. Crashing. I know you guys were watching the video and said, oh, I got enough information to do my homework. But right after that would have been the crashing example. And if you skipped it, I don't want you to fall apart on this quiz. So I want to quickly talk about it. Do I have enough time?
Yeah.
Okay, you ready? Here's my hints for crashing. Only a crashing problem is going to give you these crash costs and times. So this is a big hint that you've got a crashing problem. All right? You ready? And if you watched the video, I said form two columns. The first column is the difference between the normal time and the crashing time. That tells you the amount, units of time, the amount of units of time that activity can be crashed. Activity A, 2. Activity B, 1. Activity C, 2. 3, 2. Now, you're not wasting time writing these numbers down because I go right at my Y constraints at that point. Y sub A less than equal to 2. Y sub B less than equal to 1. Y sub C less than equal to 2. Y sub D less than equal to 3, right? The difference between the normal and crash time are all your Y constraints. They're out of the way. Now, your objective function. That's the second column. You take the difference, the additional money you'd have to spend to crash this activity, and divide it by the number of units that you'll be able to get for spending that extra money. 5,000 and 8,000 have a difference of 3,000 divided by 2 units of crashing. So what did I say? 3,000 divided by 2 is 1,500. Is that right? Okay, 1,500 per 1 unit crash. Here's the beginning of my objective function. Min 1,500 Y sub A. Plus, you do this for B and C. You get, that's your next column. You're literally writing your objective function. Notice, nothing but Y variables in the objective function. And the Y constraints, Y sub A less than equal to 2. Y sub B less than equal to 1. Blah, blah, blah. Now, every activity has also an X variable. These are the Y variables. The X variables are used for the activity constraints. But if you watch the video, I really push the logic behind writing these, because if you have this logic down, you can write every activity constraint with no problem, with no errors. The logic is, and if you forget, if I go too fast, check the video. The logic is, it's the X variable for the activity you're writing this for. We'll start with A. Again, you start with the X variable for the activity you're writing the constraint for. Always greater than equal the X variable of whatever precedes it. Unless there's nothing that precedes it, you put a 0 then. So it's the X variable for whatever activity precedes the one you're writing this for. And if there's no activity preceding it, you put a 0. Then you add the normal time for the activity you're writing it for. How much time is the normal time for activity A? 5 minus the Y variable for the activity you're writing this for. This little letter should always match that little letter. The activity you're writing it for, X, and the activity you're writing it for, Y. Let me repeat it. X variable for whatever activity you're writing this constraint for, greater than or equal to the X variable, whatever activity precedes it. If there's no activity preceding it, 0, plus the normal time for the activity you're writing it for, minus the Y variable for the activity you're writing it for. And if this was a quiz, it might say, for the first two, apply algebra. I can't have, Christy, you ready? I can't have, was it 5? I can't have variables on the right side. This would also be a variable if it were preceded by another activity. So in this case, I got to add Y sub A and join my two numbers together, so I get X sub A plus Y sub A. I'm adding Y sub A on both sides, greater than or equal to 5. Algebra is applied, nothing but numbers on the right, all variables are on the left. That's all I'm asking for. All of these are just adding or subtracting one or two things. That's all it is. Apply the algebra. And I'm not saying every one of them, maybe one, two. Let's do another one. I want to make sure you get this. Talk me through activity C. What do I start with? Y sub C?
X sub C.
Thank you, Sean. X sub C, then what?
Greater than or equal.
Greater than equal to what?
The one that precedes it.
Which is what? Which is what right here.
X sub A.
X sub A, X variable for whatever precedes it. Plus or minus?
Plus.
Plus, what's here? 8 is the normal time for C. Then what? Minus or plus? Minus Y sub
C.
That's how easy. You get that logic down, you can write it for every one of these. Just the logic is all you need to remember. You'll put the right things in place. Let's apply algebra real quick. Minus X sub A on both sides, plus Y sub C on both sides. X sub C minus X sub A plus Y sub C greater than equal to 8. Everybody okay? We're not done. We're almost there. You've got the Y constraints, you've got the objective function, which is always, the whole thing with crashing is, what's the least we gotta spend to get it done faster? It always costs money. So it's always a minimize. Are you ready? We're doing activity D. Let's talk me through it. You don't have to. X sub D greater than equal to, what goes here? Hello? What? What? Which is it? X sub A or X sub B? You can't do both in one constraint. Anytime there's more than one activity preceding an activity, you have to write the number of constraints for every activity that precedes it. So we have 2 D constraints. You ready? X sub D greater than equal to X sub A plus, what's the normal time? What's the normal time? 5 minus Y sub D. X sub D greater than equal to X sub B plus 5 minus Y sub D. Exact same constraints except for you have an X sub A and an X sub B. It's the only difference because it's preceded by 2 activities. E will have 2 constraints. G will have 2 constraints. H will have 3 constraints. 2, just like these, any activities that don't precede any other activities, which would go directly to the finish, you have to make the X variable of that activity less than equal to whatever you're being asked to crash the project to. That's the only less than equal, I think. No, all the Y ones are. So let me review this. This is because I know a lot of you, but it looks on your face, this is kind of the first time you may have seen it. So let me review it real quick. You like that? These guys are where was that? Okay, ready? Here's my X constraints. Whoops, A's up there. There's B. Neither one of A or B are preceded by any, so there's zeros there. C has A, D has A, D has B. Here's both E's. F has C, G has a D, and G has an F. There's H with the E, H with the G. H is the only activity that is not preceding another activity less than equal to 9. If there were another activity not preceding, you'd have to do that one less than equal to 9 also. The story says crash this to 9 units of time. It's currently going to take 12 or something. Okay? Here's the Y constraints. Y sub A less than equal to 2. B 1, C 2. All the differences between normal time and the crash time. This is the number of units of time each activity could be crashed. These are less than equal. Applying some algebra to a few of them. Is that it? I covered all. Where's the objective function?
Up top.
Did we already talk about it? There it is. Minimize 15,000 A, 1,000 B, 1,000 C. The number one mistake with an objective function is somebody will take the difference between normal cost and crash cost and write this forgetting to divide by the number of units that it will be able to crash at that cost. You want the crashing cost per 1 unit in this objective function. Everybody hear that? I think that's it. See you at the quiz. Let me take a time. What happened? We're still talking? Casey's absent.
Will you post this?
It's posted.
When? did you post it? Because I look at all this stuff all day long, and then when I get here, like, it's posted.
When I get up in